Let's see, anything else? Okay, no, not everyone started right at the beginning, so I'm just going to give you another minute to see if you can work this one out, and then we'll go over the answers. All right, well, let's go ahead and see how you did with this. And there are a couple of questions on this that weren't on your Newton homework, but I think you could probably figure them out. I'm curious to find out if you did. So slope, I think you know what slope is. Let's go ahead and write that down. That's this, whoops, nope, wrong one. I'm used to it coming first. Probably you are as well. So it would be 0.83. That's the slope. The correlation coefficient isn't the slope, by the way. Correlation coefficient just tells you whether there's a relationship. It doesn't say whether how steep the relationship is. It does say if it's up or down, but anyway, interpret the slope. So this is the one that wasn't part of your homework, but you had questions about the y-intercept. I figured, well, you can handle slope probably. So what that means, let's see, what is this referring to? It's referring to this line. So I'll talk you through this one. The second one I'll do much more quickly. So this line here represents the relationship between years of private music instruction and ACT scores. So what that means is that for every year of private music instruction that you receive, you should expect your ACT score to go up about 0.83 points. So not a whole bunch, but every year counts, right? So you could write it in a bunch of different ways. I'll be super precise, but anything that says that you recognize that it's the relationship between the years of private music instruction and ACT score. Like I said, I'm going to be super specific, but if you just said anything related to this relationship between those two, then I would probably be super happy if I were actually scoring this myself, given that you didn't have any questions that were quite like this on your homework. So let me write it down myself, that every year of music instruction results in an additional 0.83 points on the ACT. That still isn't the greatest wording. Really, it should say something like, predicting. You're predicting this much, because it's not reality. Of course, there are people who had no music instruction and did really well, and some people who can play the harpsichord with incredible skill and got a really bad ACT score. So this is just a prediction. So I probably should have had that in there. But if you had anything saying that there was a relationship, then that relationship meant that the more music instruction you got, the better, or in terms of your ACT score, then that's great. Now this was on your homework. You did have a question or several questions like this. Y-intercept, that one is going to be just 21. It's just the y-intercept of that line up there. So hopefully you remember this from algebra class back in 8th grade or whenever it was you had algebra class. And then what does this mean? What this means is that we predict, here I'll write it down. This is sort of like what Newton had in their answers. They said something like, we predict that someone with no music would get 21 ACT or something like that. So I forget. It was a multiple choice. You remember if you did the homework, which some of you did, hopefully most of you did. But it was something like that, that we're predicting that someone with no music instruction would get a 21. And of course, that's not, it's a prediction, and it's based on statistics, and statistics aren't perfect. So you never prove anything with statistics, and it wouldn't surprise me if someone with no music instruction could get a 36, the perfect score. Okay, what's the best predicted ACT score for a student with 3 years of private music instruction? So we would use that formula and just do 21 plus 0.83 times 3. And so this came from that formula up at the top. I can't do this in my head, so I'm going to have to pull out my calculator. Give me a sec here. And I got 23.49. And I realize that that's a decimal, and you don't get decimals on the ACT score, but as with a lot of statistics, we don't care. We're going to write it down like that. That's my prediction, which is kind of halfway between 23 and 24. So if someone got either a 23 or a 24 with 3 years of private music instruction, I'd call that a win. Okay, second one, a little bit quicker. We'll do this. And so explain why the y-intercept is not feasible. So the y-intercept is negative, which you have to bear in mind what this is referring to. We're predicting the amount of time it takes for the next eruption based on the length of the current eruption. Now, if you've ever been to Yellowstone National Park, this is what the park rangers do. Whenever Old Faithful erupts, they take a stopwatch and they time it, and they actually have a formula similar to this. Maybe it's actually more complicated than this, but it's a formula, and they use that to predict when the next one is going to happen. And so that's why if you ever go to Yellowstone and go to Old Faithful, there's a sign that says next eruption at approximately 2:30 p.m. And it'll be about 2:30 p.m. that the next time Old Faithful goes, because it's that predictable, it's faithful. But anyway, getting back to this. Why is this not feasible? It's because y here, so x is the amount of time of the eruption. Y is the amount of time until the next eruption. So imagine what the y-intercept would mean. You could use any of these arguments to say that this is not feasible. First of all, it would mean that you're putting in 0 for x, which is an eruption that lasts no time. Well, that's not an eruption, right? So that's one way to say that it's not feasible. The way that the book, or not the book, Newton, they focus mostly on the fact that it's negative, and so that would be predicting that your next eruption is going to happen in the past, which doesn't make any sense. So yeah, the y-intercept is negative. Negative means, so I'd probably write something like this, means that the next, let's see, the prediction is that the next eruption is in the past. So, like saying that the next exam that you're going to have is 2 weeks ago. That doesn't make any sense to say that the next one is going to happen sometime in the past. Okay, now we can use this. What is the best predicted time for the interval after an eruption that lasts 315 seconds? So we have negative 4.7393 plus 0.283 times 315 is what you're doing on your calculator. Give me a sec. I didn't do this earlier. I should have, but I didn't. I was goofing off up here. Whoops. 7393 plus 0.283. Okay, I've got it. I've got 84. 84 point, is that a 4? My calculator is, I think it's a 4. So minutes. So it'll be about an hour and 15 minutes. Wait, no, an hour and 25 minutes. About an hour and 25 minutes until the next eruption. This is literally what those park rangers do. Is they do this, they time, they calculate, they put it down, and they put it on the sign. Okay, so did we do it? We did it all. Any questions? So did you get an A? I'm sure you did. Put an A at the top, put a star, whatever it makes you feel better about yourself. Okay, we need to switch gears here. Give me a sec. Pull up PowerPoint. There it is, chi-squared. Okay, so I have this here. I want to point out that I know when you're looking at this, you want to say chi, right? You want to say chi or chai, or I don't know what you're going to say, but this is chi. It's a Greek letter, chi. All right, so I'm going to say chi. You can say whatever you want. You can call it chi if you want, but it's chi. It's chi. It rhymes with I, and it's like sky without the S. Chi. So just think that, chi. I know I'm battling against the English, or not English language, but the way that English speakers pronounce things whenever I try to get you to pronounce a Greek letter correctly, like mu and chi. But that's what it is, it's chi. And so if you go into your advanced research methods in psychology class and you start talking about chi squared, your professor's going to think you're an idiot. So don't do it. Just think sky, chi, sky. Good. You've got it now. So this is chi squared. It's this Greek letter squared. What does it mean? What is it about? Well, let me get this, get an example here really quickly. Where is it? Okay, this comes in 3 major flavors, and we're only going to study 2 of them. But what this is it's a statistical test that allows us to compare qualitative data. Qualitative, these are things that have categories. Categories, right? So I'll show you some categories. I've got some categories up here. You know what these are because you've been looking at that other sheet and you're thinking, oh, do I get it? Yes, you do. You do get M&Ms today. But anyway, getting back to this, chi-squared, it allows us to compare qualitative or categorical data. Comes in 3 major flavors, just like M&Ms. Actually, M&Ms comes in like a dozen flavors, but 3 major flavors, right? You've got peanut, regular, and okay, peanut and regular too. But anyway, yeah, just like chi-squared, we're going to focus on 2 major flavors here. The goodness of fit test. That's what we do today is goodness of fit. Goodness of fit. Okay, so goodness of fit. And then on Wednesday, we'll do what's called the test for independence. That's the 2nd major flavor. Those are the 2 flavors that we're going to worry about. And then the 3rd one, just in case it pops up, I can't remember if it shows up in, in Newton, they have some multiple choice questions that they might be asking you. It's this so-called test for homogeneity. Oh, bless you. Someone's brought back some disease with them. Yeah, so just stay away from that person. But anyway, getting back to goodness of fit. So what is goodness of fit? Let me explain in terms of these M&Ms. M&Ms, do they come in like the same proportions for all the colors? You see all the colors there? Are all colors represented in the same proportions? Like there's the same number of blue and red and green? Is that the case? Well, that's what we can check with goodness of fit. What we're asking is a particular set of percentages a good fit for my data? So and this is actually what we're going to do in a minute, is I'm going to say, I think that you have the same number of blue and red and orange and yellow, that they're all the same. There's no difference in the way that M&M's Mars manufactures their M&Ms. So that's goodness of fit. You can also use goodness of fit to compare like percentages, like you think that there's twice as many browns as oranges or something like that. But anyway, that's goodness of fit. You have some percentages. You want to say, are they a good fit for your data? Independence. Independence, and I really don't have a good example of this because what this is, so this is peanut, this is plain. This is really a test for homogeneity. Homogeneity just means, are they the same? Are the proportions the same between peanut and plain? However, independence is basically the same thing, but if you had 3 flavors. I didn't bother buying 3 flavors because I was too lazy. So you only have 2 flavors to choose from today. So we're going to use the test for independence with 2 flavors, even though test for homogeneity is really, it's the same thing. You get the same result, just philosophically, it's kind of a test for homogeneity. But anyway, that we'll do on Wednesday. So today, though, we're going to be doing the test for goodness of fit. So as a warm-up, well, here, before we get the warm-up, let us do this to get you nice and scared about this situation. Lots of stuff here. So Oh yeah, degrees of freedom. Okay, sorry. I was trying to think, what am I doing here? Okay, so the chi-squared distribution is a distribution that looks something like this, and it's this weird skewed distribution. It depends upon the degrees of freedom. Degrees of freedom has to do with the number of categories we're comparing. I'll explain in just a minute, but here's just a couple of examples of chi-squared curves. They're very skewed. This one, the higher the degrees of freedom, the more it's going to look like a normal curve, but we generally don't deal with high degrees of freedom with chi-squared, which you'll find out why in just a minute. So degrees of freedom 2, you have this very skewed distribution. 3 and 4 are going to have maybe a hump very close to the y-axis and then skewed out here. The mean, if you're curious, we're not going to use this, but here I've got it here anyway apparently, is if you know how many degrees of freedom you have. For example, with the M&Ms, there are 6 categories and 5 degrees of freedom. So 5 degrees of freedom, I know it's confusing, the degrees of freedom thing, but 5 degrees of freedom. So the chi-squared curve for the M&Ms, actually the mean of that is going to be 5. And the standard deviation of this curve will be the square root of 10. These curves are always positive. I mean, this is more, that stuff, all of those symbols are more just my mathematical, I'm just interested in this because it's fun for me, not so much for you. These are non-symmetrical, skewed to the right. The mean is located just to the right of whatever peak there is, which there will be a peak, and the total area is 1. Just like the normal curve, just like the other curves that we're used to, the t distribution. So this is finally something other than z or t that we're going to be using to figure out the answer to a statistical test. So I've already showed you these pictures, but I do need to show you this because even though we have Excel, the Newton still is living in the dark ages, and so we have to talk about this thing here. I know that we've been suffering with Newton and having things referring to tables that are non-existent. I believe that tables exist in Newton for this one, and this is what the tables look like. So let me just explain briefly what this table means. So what this table is this is a table of critical values. What that means is this is the cutoff. That if you're interested in an alpha level of 0.05, for example, and you have 7 degrees of freedom, then the cutoff is 14, about 14. That would be here on that curve, and the 0.05 would represent this area here. The way that we're going to use this is we're going to compute, well, actually, yeah, we'll compute a p-value, but we'll also compute this. But you're going to compute a chi-squared value. We'll do this momentarily. It's not difficult, actually. Then once we have that chi-squared value, you compare it to the numbers in this table, and if your number is bigger than these numbers, it means that you reject the null hypothesis, etc., etc. And if it's smaller, it means you're back here in normal land, like, well, it's not very exciting. So you have to have something that's really different from what you would expect in order for the thing to actually pass or reject the null hypothesis. Okay, so where do we get chi-squared? Now I'm going to show you a formula. It's scary, but I'm going to walk you through it. Don't worry. So this is the formula for chi-squared goodness of fit test. We're going to do this momentarily with this class, and then we'll do M&Ms. So the first thing to note is that you're adding some stuff up. So I'm going to add up a bunch of stuff. That's what that big sigma is. What are we adding up? We're adding up these things. Now, what is this stuff? Well, this is the expected stuff minus the observed stuff squared over the expected stuff. I know, that's really confusing. And so because it's so confusing, I have made a table for you, and that table is right here. So this piece of paper, everyone's got this piece of paper, I hope? So this piece of paper is the one that will show you how to do this, or at least we can walk through this together. Okay, so let me, just a sec. Here we go. Okay, first of all, I need to explain what our hypothesis test is. You have this claim. I just realized I did not check my microphone. It's been working. Oh, good, it's still, usually if I don't check it, then it turns out that it's not on. No, it's on. Okay, so I have this claim. I think that the population of statistics students is not evenly distributed among classes. And what I mean by class is what you are classified as according to the registrar. There are CCP, post-secondary, freshmen, sophomore, juniors, and seniors. Now I have a sample of statistics students here. So that's my claim. So let's write down the hypotheses. Oh, here, the hypotheses are this. Let's see, test for goodness of fit. Here we go. Goodness of fit. Yeah, the population fits the given distribution. Okay, so I guess what I should say for my null hypothesis is that the null hypothesis is that all classifications represent 1/5 of the population. So the null hypothesis is that the percentages, the proportions, whatever it is, the thing that we're studying, they are a good fit. And so by a good fit, I mean that everyone is equal. At least in this case, you might have another one where you'd be studying some other claim, but here, everyone is equal would be the claim, or not the claim, that's the null hypothesis. And then the alternative is basically what the claim says. Not always, I should say, don't fall down that trap again. But the alternative is that not all classifications are 1/5. Da, da, da. Okay, just let me back up one more time to show you, to contrast this with the sort of the template. The template that we're using is that null hypothesis is the population is fits whatever distribution. So in this case, I'm saying everyone's the same, 20% for everyone. And then it does not fit is the alternative. So whatever it is that we're talking about, and today it'll always be an even distribution, in this case 1/5 for everyone. Now that we've got this, let's see, we can talk about left-tailed, right. Oh, there is no tail. So you don't have to worry about tails. If you insist, I would call this a right-tailed test, but not necessary. So we're not going to call it tails or no tails. We don't have to worry about that. Alpha, we need an alpha level. Alpha is 0.05, at least for this one. So we'll use 0.05. And now the distribution. The distribution that we use is the chi-squared distribution. Remember, sky rhymes with I, chi. You can do it. I know you can pronounce this correctly. If you ever talk to me, I know you're not going to have to, because you're just going to write it down. But in your brain, when you hear it, you know what it means. Okay, let's get to the data. So here's the actual data. And I'm going to toggle back and forth just a little bit between the actual data, which you have on that piece of paper, and this little formula here. So here's what I've done is on my table, I've tried to lay things out so that it's easy for you, so that it works out nicely. So you'll notice that I have to do the expected numbers minus the observed numbers and square them. So in my table, I have observed, I call them F sub O, that's the observed frequencies. Now let's talk about the expected frequencies. I'll bet you can figure this out. So I'm just going to pick someone randomly and ask, what would you expect if my null hypothesis were true? You're not here, sadly, but you would know. Diego, what would you expect to find in terms of these numbers if everyone was equal? 5, right? You'd expect to see a bunch of 5s. How did you get 5? Divide by 5, you get 5 for each one. By the way, I got lucky here. I have 25 students. And so divided by 5, I get a nice even number. If I had 24 students, I wouldn't have a nice even number, but I would still write it down. I'd have 4.8 for each of these, and that would be fine. It's okay to have decimals, but I was so relieved. Honestly, I felt so good when I saw that this worked out evenly. So if you have a decimal, it's okay. It just makes the calculations a little bit yuckier. But 5s are beautiful. So it's 1/5 of 25. 5 for each one of these. Beautiful. So that's what you're going to put in that big brick there, which I know yours, I probably could have shrunk this down a little bit, but I didn't. It's huge. Okay, next, going back to the formula, you'll notice that you do the expected minus the observed and you square it. I've done this on 2 lines. The first thing is expected, I've got observed minus expected. It's the same idea. Here, if it bothers you, you can do expected minus observed, but it's not going to matter in the end. So I'm going to just subtract downward. 7 minus 5 is 2. 6 minus 5 is 2. And if those were decimals, I'd have a decimal down here. If that was 4.8, I would do 6 minus 4.8, and I'd get 2.2. And I would be annoyed because it's going to make things ugly in the future. But for us, it's going to be beautiful. 6 minus 5 is 1. 5 minus 5 is 0. 1 minus 5 is negative 4. So far, so good? Yeah, what do you think, Lily? Oh, how did I do that? I spoke and wrote, and I was thinking about the M&Ms. Sorry about that. 6 minus 5 is 1. Let me just take another deep breath. It's better. Okay, after I was bragging about how the numbers are going to work out so nicely. Thank you, though. Yeah, keep me in line here because I mess things up more frequently than I should. Now you're going to square this. So that's what this line is for, is you're going to square those. So this is going to be 2 squared is 4. And of course, if it was 2.2, you'd punch it into your calculator and you'd do 2.2 squared, and then you'd get angry because you'd have a big ugly decimal. But fortunately for us, we don't. 1 squared is 1, 1 squared is 1, 0 squared is 0, and 4 squared is 16. I know it's negative 4, but negative squared becomes a positive number. We're almost done. Now all we do is take that line, divide it by the expected line. So each of these gets divided by 5. Here we'll get some fractions, but don't fret. It's going to be all right. Okay, so here we go. We're going to do this 4 over 5. This is 1 over 5, 1 over 5, 0 over 5, and 16 over 5. All right, we're almost there. Final step is we take all of these and add them up, and that becomes chi-squared. I know it's like the z distribution is sort of mysterious, the t distribution is mysterious, but chi-squared, it's easy. You see the formulas, you get your answer. So add those up, get the total, and that's going to be 22 fifths. 22 fifths, which I know you're going to do on your calculator and get 4.4. Yeah, 4.4. So 4.4 is chi-squared. All right, let me go. I'm going to go back. Well, let me just make sure that we're all good with this and see what we have. See if you have any questions so far. All right, let me see. Do I have my full table? I just realized. Oh, no. Do I not have the full table? Oh, I don't have the full table. I don't know why I don't have the full table, but okay. We're going to pretend that I have the full table, all right? That's sad. Okay, well, let's go back to, where is it? There it is. Okay, so our distribution is chi-squared, and if you noticed, we computed chi-squared is equal to 4.4. Now, what does this mean? What's our conclusion? Well, we would compute, here are the options. Either you're going to compute a p-value, and that we would do on Excel, or you can find the critical number, critical value, and this is the table. So I'm not going to do either, I guess, at this moment. Well, I'm going to cheat. I'm going to pretend to do the critical value. I don't know why I don't have, here, let me go back to this just a second. So in order to do the critical value, we have to compute the degrees of freedom. The degrees of freedom is equal to the categories minus 1. So in our case, there are 5 categories. Minus 1 becomes 4 for the degrees of freedom. So the degrees of freedom is going to be 5 minus 1, which is 4. Okay, so what I would do now, although I can't really because I don't see my table anywhere and I don't want to take the time to look it up, but we're going to pretend, all right? So I would go to this table and I would find the degrees of freedom 4, and I would go over here to this column and I would look for the number. I'm just going to pretend that that's the number in the table, and that's what I would get for my critical number. I would use this column because that is my alpha level. I can say for sure that it's going to be somewhere in that range. I just don't know it offhand. I don't have this table memorized. And I left out part of the table because I don't know why I left it out. I should have put it in. Okay, well, let's go over to this and we will pretend. What did I have? What's my fake? So this is fake, 5.932. Okay, so critical value. The critical value, which I will write like this, chi-squared crit is 5.732 or whatever I said. And you'll notice that this is smaller. It's smaller than that, which means that that chi-squared value it's not good enough to reject the null hypothesis. So sort of the way that you might picture this is that this number is right here, and our test statistic is back here. So not very exciting. 4.4 is not exciting enough to say that we're going to reject the null hypothesis. So if it's bigger than the critical value, then you reject the null hypothesis. If it's smaller, you don't. So I fail to reject the null hypothesis, and I say that there is not enough evidence to suggest that the population of statistics students is not evenly distributed among the classes, or something to that effect. So remember, it's always the same. You always say that there's not enough evidence for the alternative when you fail to reject the null hypothesis. Okay. All right, on to the M&Ms. So, before we do the M&Ms, I need to assure you that, here we go. Let's see if this will do this. Give me a sec. It's waiting. Come on, buddy. Okay, I want to assure you that I was very, what is it called? Sterile? I was, let me see if I can find this. I thought I airdropped it to myself. Just a sec. That I was hygienic when I did this. Oh, here it is. There we go. Oh yeah, it's up there. Okay, so here it is. It's yesterday. Is me measuring out 1 serving size of M&Ms. And so you can see I've got all the bags. So all these bags, I'm using gloves, so you don't have to worry. I held my breath the whole time, so you don't have to worry about that as well. But anyway, that's where this came from. Okay, we don't need to watch it a second time. I should say I actually was a little bit more generous with you. I gave you between 31 and 34 grams, and a serving size is 28 grams. And I was thinking to myself that I actually gave you a little bit more than you deserved, maybe about 5 M&Ms more. So maybe while you're filling out your end of course surveys, you could be a little generous with me. 5 is the right answer. Anyway, there are peanut and plain in each of these containers. Just take one, and you don't have to open it up, but don't eat it. Actually, don't open it. That's why I put them in clear baggies. Yeah, take one, pass them around. And I'll come back in a minute. So essentially, while they're passing that around, let's set up the M&M hypothesis test that we're about to do. So give me a sec. I need to set this up myself. Okay, good enough. Copy and delete. Yeah, so if you want peanut, there should be enough. If you want plain, there should be enough that most people should be able to get what they want. There we go. That's beautiful. Okay, so while you're sorting it out, and I'll come back and get the extras in just a minute, let's set up the hypotheses. So first of all, the claim. You might wonder, what is my claim? My claim is that all colors are the same. Okay. So basically, all colors exist in the same proportions is my claim. So let's go ahead and let's see. The null hypothesis is that all colors are 1/6 of the population. And the alternative hypothesis is that not all colors are 1/6, or maybe that some of the colors are more frequent than the others, and so forth. So we want to set that up first before we start counting. Then the second thing we're going to do is we have to decide on our alpha level, and we're going to use alpha is equal to 0.10. I know that's really big, but I want at least someone to reject their null hypothesis in here. We'll see. Hopefully someone will. I'll write down degrees of freedom as well. Degrees of freedom are going to be 6 because there's 6 colors, 6 categories, 6 minus 1, which is 5. 5 degrees of freedom. So who has my bag? Oh, here it is. You got it. Yeah, send it over so I can collect. Did everyone get the flavor that they wanted? Oh, and also another reason. Oh, you need 2 flavors? You only need 1. Yeah, you only want peanut. Okay. Yeah, you can have plain. Yeah. You only need 1. Okay, so I gave it to you in a baggie for a couple of reasons. One is because you might not want to eat M&Ms at this hour of the day, so you can save them for later. Secondly, it allows you to easily count without opening the bag. And then if you decide you don't want them at all, maybe like me, you're allergic to chocolate, which I am, so I can't eat any of these, you would give them to your special friend, which I will do if there are any left over. So anyway, you can count these. I will count mine and keep track of what flavor you have. So I have plain. So make sure you keep track at the top. Do you have plain or do you have peanut? And then if you want to, just go ahead and fill out the whole table. If you're stuck though, I will help you. So I'll talk you through this. And you might ask, what do I do with half M&Ms? I've got a half M&M here. I don't care. You decide. I'm going to count that as 1 M&M. I know it's half an M&M, but I'm going to count it as 1. So you can do the same if you'd like, or you can reject any half M&Ms. Same thing goes with the Siamese twins, like with the peanut M&Ms. Sometimes there's 2 stuck together. You can choose what to do. I don't care. 3, 6, 5, 7. Okay. I'm just going to take a picture of my bag so that the people who are sad because they aren't here will feel even sadder. Just a minute. Okay. There. Isn't that beautiful? Got my bag. There. Now it's going back into the population. It's like catch and release with fish. So if you have counted and filled out your table, at least the top line, if you're dying to have that sugar high, that rush that you've been waiting for, you can go ahead and consume. But now I'm going to walk through. If you know what to do, you can just ignore me. I'm going to go through mine. You can do the same for yours. So I first am going to compute my total. And let's see, 10, 20, 37. I've got 37 M&Ms. If you have plain M&Ms, you should have between 30 and 40. Probably no one's got lower than 30, but if you do, sorry, I gypped you. I tried. You saw I measured. I actually measured on the scale. I don't know about the peanut. There are fewer for peanut. Now here we have a situation where if you have peanut M&Ms, technically you aren't allowed to use chi-squared if you have any zeros. But we're going to ignore that. I know it's kind of rude of me, but I'm going to ignore that little fact. But you're not supposed to use chi-squared under certain circumstances, and one of those is if there are zeros. But we're going to, we'll ignore it for now. It's okay. So now I'm going to do the expected value. Now everyone, well not everyone, but most of you will have different expected values. The way I'm going to get this is I take my total, 37, and I'm sad because it's not 36, but that's the way life is. And I divide by 6, and I get 6.167. What an ugly number. So actually it's 1.6666667, but I'm going to go with this. So you're going to do whatever number you have for your total and divide it by 6 and put it down where I've got my 6.167s. The next thing I'm going to do is I'm going to subtract the observed from the expected, or vice versa. It doesn't really matter, but I'm going to do 3 minus 6.167, and then I'll shut up and do the rest of them. So this is negative 3.167. Oh, whoops, messed up. What am I doing? I blew it. Sorry. Okay, so I shouldn't talk and calculate at the same time. I was trying to do it in my head, now I think I've successfully done my subtraction. So I took the top line, subtracted off the next line, I got this. That's what I've got. Now we'll square each of those numbers. So this I definitely will have to shut up and do it. Now, if you're confused or don't know what to do, you can always let me know and I'll come help you, or ask your friend, because some of you are more comfortable with your friends than with me. That's fine. But anyway, I've taken those numbers, I've squared them. Next, I'm going to divide each of these by my expected frequencies. So I divide it by the number that's just above it. So let's see if I can do that successfully. So I'll just talk you through the first one and then I'll shut up. 10.03 divided by 6.167. And I got 1.63. I'm rounding, by the way. I'm just... Okay, so the final step, which some of you probably have finished already, is I'm going to add these up. So these numbers get added up, and they go over there. And that'll be my final chi-squared value. Whew, okay, phew. So I got 5.98. I'm guessing that some of you got closer to 0. Some of you have a number bigger than my number. But we each have a number, and that number is a chi-squared value that we're going to compare to the critical value. So we may have different conclusions, which is fine. This is the way statistics works, is that if I do an experiment, my experiment may get a different result than yours because the p-value says that 10% of the time, or rather the alpha level, 10% of the time, if there isn't any effect or any, like if it's just random chance, 10% of the time you're going to think that something weird is going on. I mean, that's the thing about statistics. You can't trust them. I mean, you can trust them as far as they go. Just be aware that nothing gets proven. And it is possible for researchers to, in good faith, get different results from the same experiment because of this randomness. Okay, we need the critical value. So let me see. Hopefully I have this on my table. Oh, come on. Why don't I have it? I don't know why I don't have this value. You know what? I'm going to just briefly, give me a sec and see if it's in. Sorry, I guess I spent too much time getting the M&Ms. You saw how long it took me to bag those up. Actually, it didn't take long at all. But I had to go to the store too. I had to go to the store on a Sunday morning at 6:30. Let's see. Give me a sec. Chi-squared, goodness of fit. Got it right here. Okay, let me just pull this up. Edit. Let me just see if I can find. Here we go. Okay, I found it. So here's this sort of a table that you're going to see when you do this in Newton. So you can see here, whoa, it's huge. Okay, so there's the table. So they always give you the portion of the table that includes the degrees of freedom that you have. And so we have 5 degrees of freedom. There are 6 colors. 6 minus 1 gives you 5. That's right, 5 is the right answer for that survey you're going to take. But anyway, 5 degrees of freedom. And so the chi-squared, since our alpha level is 0.1, chi-squared is 9.236. So let me write that down over here. 9.236 chi-squared 9.236. Okay, so here's what we do now. Whoops, you can't see my answer. There it is. So now what you're going to do is you're going to compare your critical value or your value with the critical value. Since mine is smaller than the critical value, it means that we're going to fail to reject the null hypothesis. So when chi-squared is less than chi-squared crit, you're going to fail to reject. And if the opposite is true, if your chi-squared value is bigger than this, then you get to reject the null. I hope someone has rejected the null hypothesis. We're going to find out here in a minute. Anyway, once I've done that, I can write down my conclusion. Timing is bad. But my conclusion is that there is not enough evidence to conclude that M&Ms are not equally distributed. M&M colors, I should have said, are not equally distributed. Now, I don't know if there are any M&M aficionados out there, but I used to, back when I could eat chocolate, eat a lot of M&Ms. And I'm pretty sure that M&Ms are not equally distributed. There are certain colors that are more frequent than other colors. In fact, back in the olden days, not anymore, M&M Mars used to actually publish the percentages that they had on their website of each of the flavors. And not only are they not equally distributed, but so some colors are more frequent than others, but also plain and peanut are different from one another. So, but I'm curious, did anyone get a chi-squared value that's bigger than 9.2? You did? You did? Are you both plain? You're plain? And you're plain? Or are you peanut? You're peanut and you got one that's bigger? What about you? You have plain and you got a bigger than, wow, so there's a few people. Now, one of the things that, the reason I'm surprised about the peanut is that peanut, you had such a small sample size that you might, it's easy it's hard to get a critical value bigger than 9.2 with a small sample size. Now, before you go, I would be very thankful if you were to share your data with me. And so to do that, as your last exercise, what you got to do is you've got to scan this. Wait, here it is. There it is. Yeah, share your results with me. So with your phone, scan that, and it's just a quick 6 questions or 7 questions. Just your flavor, your gender. I know. I was just curious if there's a relationship between plain peanut and your gender. And then the colors. So your color distribution, you'll see it's really easy to fill in. So if you would do that for me, that'd be great. If you don't have a phone or if you don't know how to scan this, I will scan it on my phone right now, and you can just fill it in on my phone. So before you leave. So either do it on your phone. So here it is. Trying. Sorry, I'm going to get in the way here. There it is. And it's coming up. Yeah, so here it is. If you need it, there's my phone. I can even put it on my iPad. And then I will bring the entire results on Wednesday because we will use them for the test for independence. Whoops, how do I do this? I will freeze. I will put it on my iPad as well if you prefer to use the iPad. I know everyone's saying, why would I need this? I have a phone. Okay. There we go. Okay, so there's two ways that you can do the survey if you want. Otherwise, have a great day. If you don't want your M&Ms and you do not know someone who would want them, you can return them. I will find someone in my office who wants them, I'm sure. But so it's up to you. You can put them here. Guess no one needs my iPad. Oh well.
Oh, that,
What's that?
that's sweet.
What?
Your vest.
Huh?
Your vest.
Oh, the vest. I thought you were talking about this beautiful QR code.
Quick, scan it, mess up the results.
No. If you really want to join the survey, though, you can take a bag of M&Ms, and only if you fill out my survey, though.
What's it for? You said count?
It's for statistics.
Oh.
Yeah, we're counting. We're counting M&Ms before we eat them in order to have joy. Okay, what am I doing here? Cancel this. Discard. Okay. What are we doing in this class? Green's theorem. That's what we're doing. Green's theorem. Okay, now we're back. Unfreeze. Unfreeze. I guess no one wanted to relinquish their M&Ms. Put these up here. I could put them in the accordion, but this is just as efficient at this point. Just spread them around. Spread the joy. Or the sorrow. How you get it. Ooh, I should give you a quiz. Me? No, everybody. Everybody wants an additional quiz. One to take. Look at these, but then you might be bored. Let me get this. Here it is. This one. This one. If you get bored, we get bored. Because I know your passions royales. Yeah. And all that. Andrew Connor. Wow. Music to get started. Oh. Wow. So everyone, did you bring back some disease with you? I know you'd like one. Limited supply. Two, three, four, 5, 6, 7, 8, 9, 10, 11. That's all I got. 3.
Oh, 2024 and 2025? Free?
They're free.
I would love them.
You have one free. It's only half a year old.
Yeah.
But you could rip out the pages that are overtaken.
Honestly.
Yeah. What else does it have in it? Is it anything important?
I used to use it in high school. Middle school.
Yeah, they used to give these to you?
Yeah.
They're trying to, hoping and dreaming that you become responsible.
We never got one of these at the start of the year.
Yeah, well, apparently because they were all sitting here. They don't have the first day of classes.
September.
Oh, this is December. This is January. January? Yeah, they don't have the first day of classes. I guess this is a generic planner that they just slapped the new logo on.
Okay. Oh, it is free.
Yeah, it is pretty cool.
The table of the elements.
Lucky guy.
Oh, it's warmed up quickly.
What?
It's warming up.
That's crazy how you can get a sweatshirt on now.
Yeah, it's I just read that. Well, I wore it and
Oh yeah, I got
started
some
sweating
sweat.
and now I'm taking it off.
I got my Sam's Club coat.
Yeah, I think that one.
It's not a Carhartt, it's a
Nice. We should have known. We should have known. From the moment that we.
Huh?
From the moment that he asked us, have you simplified why? And why? And then he didn't
Oh,
do it.
that's not
He did it wrong.
It's just a slide.
It's just like.
Oh yeah, the first part.
Actually, I should have known when.
I think I had one. I don't think it's like
We're breaking this down.
I'm not too sure.
I mean, it's not due till Friday, so this constructor sucks.
So you can figure out.
That was what we had.
Oh, this is the first. No, wait, this is. We did this first. I want to do this.
I don't know. I've been staring at it for like 10 minutes. Okay, so unless it's green, out of luck. No, it wasn't green.
I will say.
So
It only looks everybody has time.
Yeah, I was gonna say, you know, it worked last year.
But last year I had in America.
Me and Matt, we both worked on our last book all the time. I love that. Actually, my last report is
So do we have to print?
yes. We've tried doing it like 3 times.
What was the printing fail?
Because it was better, but and then it just stopped.
Oh,
It's like they completely did the petition.
I guess going to check.
But I need to work on the
Oh, I have to do that.
Where am I going? I'm going back to my room.
It's not bad.
It's just
It was only 18 problems.
I just
Like 18 homework problems or 18 problems to test? 18 homework.
actually like to
How did you test it? You tested yourself.
that's not
There's no way to sit down. The tests are so it's just basic stuff in class. That's what we're saying our last time. So
Yeah, it was like 2 all afternoon when we were making sure.
every week.
I didn't know I didn't do. I didn't get all that from mine. It's just all like what?
So you just have to go pretty much.
So what?
I made sure that I would do my calls during break. It's like I worked beforehand to make sure I didn't have it. So that's what I did tonight. So it's just I actually got this. I'm proud of myself. Yeah, I knew that I'd probably be a little busier this week if I did it as well. But I was like, you know, that's a sacrifice.
All right, let's see who's here. Oh, everyone. All right, hey, everyone's here, so let's get started. The sooner we start, the sooner we can finish and go get good seats because whatever the Goliards now call themselves, they're singing in chapel today, so you want to get good seats for that. So let's pray for our week, 1 week to go. Is there anything special going on this week that we should be cognizant of?
Research is this week.
Oh, your research? What?
Pre-circ.
Pre-circ.
It's where
Oh,
we
it
talk
is
about-
research.
Yeah,
Pre-circ. Ah, I love it. So you have to talk about things?
we have to talk about what we're gonna do for our honors project. So
Ah, okay.
I don't think it's gonna be that scary, but like,
Yeah,
it's still a little bit scary.
pre-circ. Nice. All right, let me go ahead and pray for us, and we'll get started. Thank you, Lord, for this day. Thank you for breaks. Thank you for this week. I pray that you would bless each of these students during this last week of the semester. Help them to do well with this last bit of work that you have ordained them to do during this season. I pray for the students that are getting ready for their honors presentations that this week, that they would be able to do a good job presenting in this sort of mock presentation, and that you bless their efforts to improve, and that they'd be able to take the constructive criticism that they get to do a better job in the spring when they do the real thing. Guide us through our lesson. Be with us throughout our day, Lord. In your name I pray. Amen. Okay, so what are we doing? Yeah. Oh, I gave you a quiz already. Yeah. Couple of things. First of all, I was going to dump all of those quizzes in the accordion thing, and I just didn't have the heart to do it this morning. So I thought, well, I can either sort them into the accordion or I could just sort them at your place. So I just did it here. That way, you can't reject them. You have to take them, apparently. So I also found this in my files. So this was just sitting there. I was like, well, we didn't do this when we were in class. So I thought, well, we could do it now. So you can take a couple minutes, see if you remember this. It's been a little bit, maybe a couple of weeks, but give it a try. See if you can remember this Jacobian while I get the rest of myself set up. Oh, and we are still recording from the first class. Well, that's nice. We don't need to record this class.